SwayamPrabha. Digital India. Educated India.
Hello, welcome everyone to today's lecture for this lecture series on modeling of multiphysics system. So, in the last 3 lectures, I believe we have covered the principles of transport phenomena, where in the first 2 lectures we looked at the heat transfer and how the heat transfer we can model for a given system based upon analytical approach and numerical approaches. Then the last lecture we talked about and introduced the concept of mass transfer. Many of you would know what mass transfer is and would realize, but it is not studied in that detail as you would study heat transfer, right. So, in this segment we have been talking about different physical systems and different physical models based upon single physics, right. So, we are not interfering one physics to another and how they are coupled, that is not what we are looking in this segment. In the next segment, in the upcoming lectures, we would move on from single physics to multiphysics, and we will see how the physics are coupled. As an engineering student and as an engineering perspective, you should be aware of the different physical phenomena and how they are modeled or considered. In the earlier times, there was no distinction between thermodynamics and solid mechanics and fluid dynamics, right. Everything was considered as mechanics and they were modeled accordingly. So, this course is relevant towards that, as we are trying to unify all the concepts of physics, whether it be electromagnetism or solid mechanics or heat transfer, mass transfer, into one unit, right. So, in this lecture we will move on towards solid mechanics, and in the upcoming we will have quite a few lectures to move on towards this concepts of solid mechanics in detail. Okay. So, let us introduce this concept for those who are unfamiliar and for those who are new to solid mechanics. It is the science or the study of a deforming body. So, we are typically looking at solids in this case. A solid body, it can be deformed under the action of external stimulus, which can be a force based stimulus or a thermal stimulus or any other stimulus. That stimulus causes the body to change from its natural state to something which is deformed or is not natural. This causes the generation of stresses in the body. The study of this body's deformation and the resultant stresses, the conditions leading to these deformations and eventually causing failure is what is covered under solid mechanics. So, by definition, so we can define solid mechanics. So, solid mechanics is a collection of laws which are physical phenomena governing equations and techniques which would define or predict the behavior, the mechanical behavior of a solid body / material under the influence of external stimulus, right, which is typically mechanical loading, mechanical, thermal, etc. Loading. All right. So, so this field, as we have talked about, it studies the deformation and all the physical phenomena and the governing equations of a body that is influenced by an external stimulus, which is either a mechanical load, means forces. It can be a thermal load, say change in temperature or temperature gradient. It can be some form of concentration variation of one species in another species in a solid medium, which causes strain in the body, right. So, all of these will fall under this category of solid mechanics. External stimulus can be of different forms, as we talked about. So, they can be mechanical forces, they can be thermal variations, they can be chemical variations. So, the chemistry of the system is changing. They can also occur due to non-homogeneity, in composition. Okay. The last one is not so common. The first three, however, can be seen very often, and these external stimulus are required to cause the stress development or the stress generation in a body. Okay. So, whenever we are doing an analysis of a solid mechanics problem, we follow the following steps. Okay. Step 1 is the analysis of strain or deformation. Okay. So, the first thing that we look up in a body is something that we can physically measure, is the strain in a body, right. So, you have this pen. If I stretch this pen, it is going to elongate. If I press this pen or compress this pen, it is going to shrink, right. This is something we can physically measure. We have tools to measure the strain or the deformation, rather the deformation is something we can measure and strain we can get out, right. So, strain, for example, I press this tip at the front and it is getting in and then it is coming out. There is a spring inside which is being compressed and then is released, right. So, these are mechanical stimulus. What we are measuring is the deformation. So, that is the first thing that we can do. We have scales, we have other devices which we can measure distance and the length contraction or the length expansion, the shape variation, the rotation of a body in a coordinate system is something we can very easily measure, right. So, that is our first objective or the first step towards solving any solid mechanics problem. You can imagine that there is a membrane like a drum and you are beating the drum with a stick. The drum is vibrating under that influence, right, and that vibration of drum is the deformation. So, you can measure that deformation and that will give you the strain in the body. The second part is your stress analysis. Right. So, this is a stress analysis and gives us the relation between. So, this relates deformation to strain. The stress analysis, it relates the forces to the stress. Okay. So, a body is subjected to physical force. I can press this down, I can bend this, I can push this pen in, and all of these stimulus, external forces are being applied. These are surface forces. Likewise, you can have volumetric forces in this, like for example, if I drop this pen, then the force acting on it is due to gravity. Likewise, you can put it into a fluid and then it is being compressed from all the sides, that is hydrostatic loading. So, that is pressure. So, there are forces acting from all directions on this body and those forces result to stress development or some internal resistance provided by the body against that external stimulus, right. So, these internal resistance are called the stress. So, relating forces to stress will be our next analysis, understanding what are the forces in the body, what kind of forces, what framework we are looking at will give us the forces, right. Then the third step is an extension to the force analysis, and that is called the conservation law. In this case, we are doing force equilibrium. Or conservation of linear momentum. Okay. So, F vector, that is a summation of all forces, is equals to mass of the body times acceleration. You have a body, you are acting forces from all directions, it is falling down, it is being compressed, it is being rotated, it is being bent. All of these forces together act on the body, and the summation of all the forces will be equals to the mass of the body times acceleration of the body. Okay, that is our force conservation or conservation law. So, we get one governing equation out of from the stress analysis. And the fourth part will be our constitutive relations. So, these are mechanical, rather material correlations that relate the strain generated due to deformation to the stress state of the body. Okay. An example of it will be our Hooke's law. So, sigma is equals to E epsilon is in the 1D format. It is actually a tensor, we have to write E in terms of C I J K L, we will talk about it later. So, Hooke's law is the relates our strain to our stress using a material property. In this case, the material property is the Young's modulus or the elastic constant. Right. So, now what we are doing, we have defined strain from deformation. So, your displacement, your deformation, that is a position that you can measure, gave you the strain, your forces gave you the stress, right, on the body, or you have an understanding of what the stress is. You have an equation which defines the acceleration of the body to the net stresses or the net forces, and then you have a way to relate that force or the stress to the deformation. So, now the last step is to bring everything together to substitute the stress by the strain using this constitutive relation and substitute the strain by deformation. And so, what we will get at the end is a net conservation equation, is a governing equation rather. In which we substitute the strain or deformation into the force conservation. That is our conservation equation. Okay. So, we substitute our strain, and in terms of strain we are substituting our deformation into our force conservation or conservation equation, and we have one equation which is in terms of deformation. Why are we doing so much or so many steps to come to this equation? This equation is called the Navier's equation. And why are we going all the steps or so far to come up to this equation, or one equation based upon deformation, is that, as I said earlier, is that deformation is something you can measure. Stresses in a body you cannot measure, There is no way to measure stress. Stress in definition is the resistance to or the internal resistance to an external stimulus, right. So, if there is a deformation in the body and it is going away from the natural state, the body will develop internal resistance, or a solid will develop an internal resistance against it. In the case of a fluid, it will flow, right. It will continuously deform, but in the case of solid, it is not going to continuously deform. It will go up to a certain point, after which it will stop, whether it is elastic or plastic, in however direction you look, until it is failing, it is going to deform and it will come to a new state, but it will stop. Why is it stopping into that final state, and why is it not flowing like a liquid? It is because that the intermolecular attraction or the bonds between the atoms can be stretched to a certain limit, and as you stretch these strings, the forces to pull it back increases with the stretch. Right. So, we can only measure, so that is your stress, but stress is something you cannot measure, it is a tensor quantity inside a body. You can measure the surface traction, that is the surface forces can be measured. However, the internal resistance that the body develops is something that is not measurable. So, there is no quantifiable way to determine or to get an equation based upon stress. Therefore, just the conservation law or the stress equation from force conservation is not sufficient to solve our equations. We need to have an equation based upon a tangible quantity, something that you can measure, and that tangible quantity is your displacement or your deformation. Therefore, we have taken two more steps from step 3 to step 5. We have included a constitutive relation which will relate our stress to our strain, and we have also substituted our strain with our deformation from our analysis of strain and deformation, that is step 1, to come up with this elegant Navier's equation. All right. So, in this lecture or in the next set of lectures that we will go over, we will do each step at a time. So, we will start with strain and deformation. If time persists today, we will go on towards stress. We will try to finish stress in the next lecture, and then we will go on towards constitutive relations, plane stress, plane strain. Using those constitutive relations, we will then finally move towards our Navier's equation. Once we have an understanding of the Navier's equation, we can then apply these. We will take two sets of examples, one is for a membrane and one is for a plate. Membranes are two dimensional bodies which are thinner in the third dimension. Plates will have some thickness, right. So, and then finally, we will take some numerical and analytical approaches to solve these problems, and if there is time, we can look into fracture mechanics and how the body fails, what are the fracture conditions or failure conditions. Okay. With that, let us start with our strain and deformation. So, let us take a coordinate system. The book that I typically follow is Solid Mechanics by Alan Bauer. So, you can search this book online. So, Alan Bauer Solid Mechanics. It is either applied solid mechanics or something, most probably applied solid mechanics or applied mechanics of solid, but the author is Alan Bauer. So, this is the book. Would like to read further. Okay. So, let us take a body which is initially at over here. If we draw it from the coordinate center, this is say x1 and x2. This is our x vector, and it has deformed and it has moved and rotated to this new point. Let us define this by y vector, and then the vector which is joining or this displacement that happened is given by the u vector, which is a function of x and t. Okay. So, we have this body A which has moved from A to A star. It has gotten a new configuration, a new body configuration. It is now at A star. Our initial vector was x vector at a given point, and the same point if we trace to the new body, and then the vector is y vector. Then how we do relate y vector to x vector is that y vector is equals to x vector plus u vector, which is a function of x and t. Okay. So, our u vector is our displacement, and so this is our displacement. Okay. U can change with position, U can change with time. All right. So, the velocity v vector will be equals to the time derivative of this, that is dy vector by dt, which is equals to du vector, since it is a partial. So, x vector is your initial, it is not going to change, y is something that will change with time, that is del u vector by del t, which is a function of x and t. Okay. If you remember your initial first few lectures on the index notation, we have looked at coordinate systems and index notation. We have written v of I was equals to del u of I by del t. Okay, this is where I is a vector, where I belongs to 3 direction 1, 2 and 3. All right. If that is comfortable, then we will define our first type of strain, well, not exactly a strain, but a kind of strain, it is called displacement gradient. So, as the name suggests, if u is a u vector is our displacement, then our displacement gradient is given by u vector dyadic with the gradient, right, and this is equals to del u I by del x j along E I and E j. Okay. This is a tensor. So, our displacement gradient is a tensor. It will have 9 components, and we are taking the derivative or the gradient of the displacement along all 3 directions on all 3 directions, right. So, you are taking u 1 as gradient along x 1 y x 2 x 3, u 2 along x 1 x 2 x 3 and u 3 along x 1 x 2 x 3, right. So, if I write this again, u vector dyadic with del, this will be del u 1 by del x 1, del u 1 by del x 2, del u 1 by del x 3, del u 2 by del x 1, del u 2 by del x 2, del u 2 by del x 3, del u 3 by del x 1, del x 2, 3 by del x 3. So, this is our displacement gradient. All right. Then the next term, so it again let us write, it is the gradient of the displacement vector along all 3 directions. Okay. You can also write this as grad of u vector. Okay. Then the next we are looking at the deformation gradient. This becomes important and we are starting to get into something interesting. So, the deformation gradient is given by f tensor, which is equals to I plus our displacement gradient, okay, which is equals to I of u vector. Okay. Let us write in terms of our index notation, f I j will be equals to del I j plus del u I by del x j. So, what we did in terms of our matrix is just we added 1 to the diagonal elements, right. So, let us write it in terms of the matrix. So, it will be 1 plus u 1 1, u 1 2, u 1 3. You remember the comma index as well, right. It is any type of gradient or derivative is given by a comma and then the next notation. Then u 2 1, u 3 1, so this is our deformation gradient. All right. So, if now we have a term that is new and that we have defined, this f we will come back again and again. Let us see if we can relate f to y somehow. If we have this y vector was equals to x vector plus u vector, if we take the derivative of this y vector with respect to x vector, then we can get our deformation gradient. So, let us write that. So, y vector was equals to u vector plus x vector plus u vector. So, f of I j is equals to d y I by d x j, which is equals to d y I d by d x j of x I plus u I. So, d x I by d x j plus del u I, because it depends on time as well, del x j, which is equals to del I j. Okay. So, that is our definition. We have our deformation gradient is the gradient of our final position vector with respect to the initial position, right. So, it is a gradient of the final position vector. So, we can relate d y I is equals to f I j d x j. This is a tensor, what it relates is our initial position vector to our final position vector. Okay. We can also invert this. So, we can say d x I is equals to f inverse I j d y j, or d x I over d y j is equals to f inverse of I j, that is the inverse of our deformation gradient. So, calculus allows inversion. So, this is possible. Okay. Now, we can look at a set of deformations, right. So, one deformation can be no volume change, and longitudinal deformation. So, we can have a body like this going on to a body like this, and therefore, we have our new coordinate system. We will have y 1 equals to lambda times x 1, y 2 equals to x 2 by root lambda, y 3 will be x 3 by root lambda. Okay. So, that is we are having longitudinal expansion. So, you are pulling it from one side and it is shrinking from the other side, but there is no volume change in this case, that is what we have assumed. So, for the no volume change we have taken the longitudinal deformation. The next one will be shear, again with no volume change. So, shear deformation can have a body like this, and it has deformed by a certain angle theta under the influence of some force, right. So, then our y 1 will be equals to x 1 plus x 2 tan theta, y 2 will be equals to x 2, and y 3 will be equals to x 3. So, this is our net shear deformation. So, then the third one could be rigid rotation. Again, there is no volume change in this case. Say that our initial body, this is our coordinate system x 1 x 2, and this goes to rigid rotation. So, it has rotated counterclockwise. So, we can say that the rotation that took place by an angle theta, and then y 1 equals to x 1 cos theta minus x 2 sin theta, y 2 equals to x 1 cos theta plus x 2 sin theta, y 3 equals to x 3. We can also have 3-dimensional rotation. We are just looking at 2D bodies, but we can also have 3D rotation, in which we have a rotation matrix, which multiply the rotation matrix to our initial position vector, we get the final position vector. In that case, there is no deformation, it is the same, that is just rotated, right. And the last one is that we can have is displacement without deformation. Again, this is rotation with rigid rotation, means that there is no deformation. So, in this case, say this is our body and this is moved along x. So, same body, so it has moved only along x. So, y1 equals to x1 plus a, y2 if it is also moved along y, it is x2 plus b, y3 equals to x3. So, our general deformation, so in general our deformation is a superposition of longitudinal plus shear deformation and rigid rotation and lateral displacement. Okay. So, we have we can have the body either stretching without changing, without having any shear. So, we can stretch and pull, that is one kind of deformation. We can have shear, that is shape change, or rotation, that is shape change, again from the same position. So, in both of the case the position is the same, it is not moved, it is just stretched. We can have the body to rotate from the same axis, it is rotating about one axis and it is getting rotated. And we can have displacement without deformation, that is a body itself without any kind of deformation is moving from one place to another place. All of these together give us a net deformation of a body, right, and that is what we are looking for. All right. So, the first kind of strain that we will talk about is our Lagrange strain and the Lagrange strain tensor. So, Lagrange strain represents the deformation of a body with respect to the initial frame of reference. Okay. So, with respect to the initial frame of reference, when we are looking at deformation, and these can be large deformation as well, then the strain that we are getting out is the Lagrange strain. Okay. By our formula is given, the Lagrange strain is given by E, capital E, and by formula E is equals to 1 by 2 F transpose dot with F minus I. Okay. So, E I j in terms of our index notation is 1 by 2 F k I F k j minus del I j. Please remember that transpose inverts index. So, it would have been I k and k j. So, if it is F transpose, then I k will become k I and the second one is just F. So, that it is F k j. All right. So, with that case let's substitute our F values. So, F I j we know is equals to del I j is del u I by del x j. We will substitute this in E I j. We get E I j is equals to 1/2 del k I plus del u k del x I multiplied with del k j del u k by del x j minus del I j. Okay. Expand this out. So, we will have del k I del k j plus del k I del u k by del x j del k j del u k by del x I del u k by del x I del u k by del x j minus del I j. This is a big expression coming up. Let's try to shorten this expression. By the property of the Kroneker's delta, del k I into del k j, it will be equals to del I j. If k are the repeating index, in the case of Kroneker's delta, it will be combined together and it will become del I j. del k I multiplied with del u k by del x j, k is a repeating index. So, you can replace k with I. So, this will be del u I by del x j. Likewise, the second one, k is again the repeating index, del k j del u k by del x I, replace k with the j, that is the second index for the Kroneker's delta. And what we will get if we solve this is E I j is equals to 1/2 of, let us write the first term, del I j del u I by del x j del u j by del x I del u k by del x I del u k by del x j minus del I j, and cancel these out, and therefore, E I j will be equals to 1/2 del u I by del x j u j by del x I plus this nonlinear term del u k by del x I del u k by del x j. Okay. So, this becomes our Lagrangian strain tensor. It is a combination of our displacement gradient, two displacement gradients, and a product of the two displacement gradient. Okay. Let us see what it represents. If we draw this on a graph, say this is our initial body, this is an element along this m vector direction, and this is our deformed body. This is the same element along this, again this m vector direction. Its initial length is L naught, this final length is L, let us say x 1 x 2. Okay. Then L is equals to L naught plus some delta L, that is our change. By definition, our Lagrangian strain along this m vector direction should be equals to L square minus L naught square by 2 L naught square. Okay. So, let us see if this comes up somehow. Okay. So, to prove this, we will start with our dxi. So, our dxi will be equals to L naught into mi. This you should agree, right? Our initial position or the change in the initial position for this element will be equals to L naught into mi along the mi direction. Okay. Then we have our dyk, which will be equals to del x k j plus del u k by del x j into dx j. Where did this come from? We know that, we know by definition, let us write it somewhere, that f of k j will be equals to dyk by dx j. So, we are finding dyk, we are taking to the left, f of k j is what we are expanding. We can substitute this del of x j from here, and we will have del k j plus del u k by del x j L naught into mi. Okay, this is j, so mj. Okay, so del k j is plus del u k by del x j L naught into mj. All right. Now, we are trying to find L square. So, L square will be dyk into dyk. Now, we have repeating index because dyk is also equals to L into mk. So, we just multiply mk 2 times, mk is a unit vector, m is a unit vector. So, L square is dyk into dyk, which is equals to del kj del uk by del xj into L naught into mj multiplied with del ki del uk by del xi L naught into mi. So, what we did is that I is the internal repeating index. So, we can change that, right. So, we can have j in this case and I in this case. K should be fixed because k is what we are producting over, we have dyk into dyk. So, k is the same. We are replacing, just we can have I both sides, but just that makes our index notation a little bit confusing, right. So, we do not want that confusion, we want one set of dyk to be separate from the other set of dyk, although it should still be dyk, right. That is why we are replacing one this j with I in this case. It will make no difference, right, because I is internally added up. Okay. So, let us go to next slide. So, we can open up our so L square therefore, will be equals to, now let us make some small things, del k j into del k I is del I j, well del j I and del j I is equals to del I j, that is a property of a Kroneker's delta, and then del k j into del u k by del x I, you will replace k with j, and in this case you will replace k with I. Okay. So, the same thing that we did earlier when we did F transpose into F. So, you will have del I j plus del u I by del x j plus del u j by del x I, del u k by del x I, del u k by del x j. Okay. Do we have a minus 1 term over here? So, we are producting these over del u k by del x k, that is it, we do not have a minus 1 term. L naught square m I m j. All right. Now, let us go to our strain definition. So, our strain definition epsilon L along m vector was equals to L square minus L naught square by 2 L naught square. So, you subtract L naught square from here and you divide by 2 L naught square, what you get is 1 by 2 of, so 1 by 2 del I j del u I by del x j del u j by del x I del u k by del x I del u k by del x j. This is the first term L naught square minus L naught square del I j. Again this is the del I j is what is repeating, m I m j whole divided by L naught square. Okay. So, we can cancel out this del I j term out, this L naught square is gone from here and we will have 1 by 2 del u I by del x j plus del u j by del x I, thus del u k by del x I del u k by del x j m I m j. This is our E I j. So, epsilon L along m direction equals to E I j m I m j, that is our Lagrange strain. In other terms, E L will be equals to m vector dot with E tensor dot with m vector, and m is again a unit vector. So, that is what we have started with, right. So, it will not change the value of the E tensor. All right. So, now we have understood what was the from a Lagrangian perspective. So, what we had was that all our strains were confined to with reference to the initial frame of reference. Now, Eulerian strain represents the deformation of a body with respect to the deformed frame of reference. Okay. This is given by E star, which is equals to 1 by 2 I minus F inverse transpose F inverse. Okay. So, E I j E star I j therefore, will be equals to 1 by 2 del I j minus F inverse of K I F inverse of K j. In terms of the value of that strain along some n vector. Now, we have replaced m vector with n vector, because m vector is along the initial frame of reference and n vector is along the deformed frame of reference, is equals to L square minus L naught square by 2 L square, which is equals to n vector dot with E star tensor dot with n vector. All right. So, this is our Eulerian strain tensor and it is with reference to the deformed state rather than the undeformed or the initial state of reference. Okay. Now, in most applications, we are not going to use our Lagrange strain or Eulerian strain, especially unless we are doing something response to large strain conditions. We do not typically use Lagrangian strain or Eulerian strain. It becomes very complicated to solve those problems. Many of our solid mechanicians would use it in terms of research. However, in practice, and in most of the engineering problems, we do not encounter very large deformations, right. In case of steel or ceramics type of material, deformations are very small compared to the original length of the body. So, if that is the case, in which your del ui by del xj is less than 1, or we have a condition of small strain, then we redefine our perspective and we rewrite our Lagrange strain vector in terms of the infinitesimal strain tensor. So, infinitesimal strain tensor also given by small e is 1/2 of your u, that is your displacement gradient, plus your displacement gradient transposed. All right. So, that is u dyadic with the gradient or the gradient of u and the transpose of the gradient of u. Let us write it in terms of gradients. So, gradient of u vector plus gradient of u vector transposed, that is our infinitesimal strain, okay, epsilon. In terms of index notation, we have epsilon I j will be equals to 1 by 2 del ui by del xj plus del uj by del xi. We can write this in terms of a matrix. So, this will be u11 1/2 of u12 plus u21 1/2 of u13 plus u31 u22 1/2 of u23 plus u32 u33. Why I am just writing the top diagonal? Because the bottom diagonal is the same as the top diagonal. So, this is a symmetric matrix. Okay. Now, this epsilon I j, what we are doing, it is a linear variant. Let us write it down over here. So, this is a linear variant of our E I j. Okay. So, if we look at E I j, let us write it in the next slide. So, if you look at E I j, it was 1/2 of del u I by del x j plus del u j by del x I. Then we had this non-linear second order term del u k by del x I, del u k by del x j. Now, we are considering that our del u I by del x j is very small. So, if it is already small, then the product of two of these terms will become even smaller, like it goes by the square root. So, it will be even smaller and we can ignore this term under this limit, and then E I j will go towards epsilon I j, which is equals to 1/2 of del u I by del x j plus del u j by del x I. Okay. So, it is a linear variant in which we are ignoring the second or the higher order term and we are just taking the linear terms. Okay. If you want to get the value of this along a given vector, so E for the small e along this m vector will be epsilon I j m I m j, and which will be equals to L minus L naught over L naught. Okay, that is the most common definition of strain that we have learned in undergraduate or even in high school, that is the change in length over original length. This is the infinitesimal strain tensor, right. It is a symmetric strain tensor in which your diagonal components, it will be equivalent to your longitudinal stretches or the longitudinal deformation, and the off diagonal component will be 1/2 of the shear stress. Okay. So, a shear stress, let us take a body again. So, if this is our body and this gets deformed some way like this, by some angle theta. So, it is deformed, there is shear deformation. Then the gamma ij will be equals to 2 times epsilon ij. So, if you look at the epsilon ij tensor, it was 1 by 2 of del ui by del xj plus del uj by del xi is 1/2 of that. The net shear strain will be 2 times of this. This will be equals to del ui by del xj, del uj by del xi, where I is not equals to j. Okay. So, we multiply it with 2 times. In the case of strain tensor, it is something that is fundamentally is the nature of the tensor. You cannot multiply that 2 within the strain tensor. However, we do need the 2 when we are finding out stresses. If you are trying to get the shear stress using the shear modulus, that shear modulus needs to incorporate that 2 multiplier, so that strain this half factor or this 2 factor can be incorporated. Right. Otherwise, you will get half of the shear stress than what it should be. So, we will talk about it when we will do constitutive relations and constitutive models, but just to keep in mind that the actual shear strain is equals to 2 times the off diagonal of the strain matrix. Okay. So, that is with understanding. Then we have our next, so this is our infinitesimal strain tensor. Then we have our infinitesimal rotation. That is given by omega ij, which is equals to 1/2 of del ui by del xj minus del uj by del xi. Okay, that is 1/2 of the gradient of u vector minus the transpose of the gradient of u vector. It was plus, this will be minus. Okay. What we get, so omega is equals to 0, 1 by 2 of u12 minus u21, 1 by 2 u13 minus u31, 0 0 by 2 u21 minus u12, 1 by 2 u23 minus u32, 1 by 2 u31 minus u13, 1 by 2 u32 minus u23. Okay. Just looking at it, we can see that this is the omega transpose equals to minus omega, which means it is a skew symmetric matrix. We do not have any longitudinal stretches, we just have these rotation terms on the off diagonals, and off diagonal components are negative of each other. So, the top diagonal is negative of the bottom diagonal. Now, if we add up both of them, so epsilon plus omega will be equals to 1/2 of your ui comma j plus uj comma I plus 1 by 2 of ui comma j minus uj comma I. This will be equals to ui comma j to del ui by del xj. All right. This is our gradient of our u vector. So, this is our displacement gradient. All right. So, if we can come back to our displacement gradient from this formulation. Now, we can write our expression that dyi was equals to dxi plus dui. dui is equals to this gradient of u into dxi dxj. So, dyi is therefore equals to dxi plus epsilon ij omega ij dxj, and this is the output we can get out from our displacement gradient. So, our final position or our final coordinate is equals to initial position plus a summation of our infinitesimal strain tensor and infinitesimal rotation tensor into dxt. Okay. Let us leave at that for our strain. There are several other strains we will be talking about. There is strain based upon stretches. You can have L square over L naught square. We can those are called the Cauchy-Green strain tensors. You could have strains due to logarithmic terms, in which there is a long strain. So you use the logarithmic strain. Several definitions of strain are there. It is in each definition of strain has some significance, depends upon the frame of reference. It does not mean that the body is changing differently, right. It is not that if I use Eulerian strain compared to Lagrangian strain, then the body has deformed differently. No, it is just our perspective of how we are looking at it, right. It is something like we are standing on the shore and we see a ship sailing, and we are on the ship sailing with the ship, right. So, in that case, if we are seeing the ship sailing, then it is moving with respect to us. If we are on the ship, then the land is moving behind and we are stationary with respect to ship, but it does not mean that the ship is not sailing. It is still the same deformation, just our perspective is different, and it has different applications based upon the constitutive relation that we use. So, strain is more a perspective or an abstract phenomena. Deformation or displacement itself is the absolute term that you can measure. Based upon that, you can select a strain that is applicable for your model, and accordingly you can select a constitutive relation and the stress that is equivalent or is equivalently applicable in that direction. So, thank you for listening to today's lecture. In the next lecture, we will go on towards the stress analysis and the force equilibrium. Thank you.